Now let's discuss about engineering stress strain curve and actual stress strain curve. The typical stress strain curve obtained through tensile test is look like this red color curve. This curve is just an approximation. It does not represent actual stress strain as per the test result. So the term used as true stress and true strain, while approximate value of the stress is called engineering stress, which is sigma E is equal to F over A naught, where A naught is the original area, and the engineering strain epsilon E, change in length to the original length, where L naught is the original length. This curve based on the original cross section area and the gauge length is called engineering stress strain curve. In engineering stress strain curve, we assume the diameter of the sample remains constant throughout the whole experiment. Engineering curve drops after ultimate tensile strength and necking, while the curve obtained based on instantaneous cross-section area and the length is called true stress strain curve. In true stress strain curve, the cross-section area does not remain constant throughout the whole experiment. The true curve always increase and rise even after the ultimate tensile strength and necking. Now the question is, then why engineers used engineering curve, not true or actual curve? The answer is, it is because of two main reasons. The first reason, it is quite difficult to measure instantaneous cross-sectional area. So most of the time during actual experiment, we do not have true stress and strain curve. Most of the time we are analyzing deformation within the elastic region. Means our area of interest is within Hooke's law, and engineering and true curves are same in this elastic region of the material. As you can see, the gray color line and the red color line both are same in elastic region. But if we are interested in plastic deformation of the material, we should use actual stress strain curve for realistic value and approach. For example, during manufacturing of the pipe or ice section beam, we have to deform the materials in a plastic region. In that case, we have to use the actual stress strain curve. Now let's discuss how to calculate engineering stress strain and actual stress strain. We know the engineering stress is equal to sigma E is equal to F over A naught, mean force over cross sectional area, which is original cross sectional area. A naught means original cross sectional area. That's why this sigma is with E. This is called the engineering stress. When we are dividing the force, whatever applied force, with the original cross sectional area, we are not taking any instantaneous cross sectional area. Similarly, the engineering strain E is equal to delta L over L naught, which is again change in length divided by the original length, because we cannot measure the instantaneous length. So that's why we are dividing it with the original length. So here the area and A naught and L naught are the original area and the original length, which is true only before necking occurs. So in instantaneous area, A is equal to A naught L naught divided by the L, and the true stress is in this case sigma T is equal to FL over A naught L naught, which is equal to F over A naught into 1 plus E, means engineering strain. So in short, we can say that sigma T is equal to sigma E into 1 plus engineering strain, as our engineering strain is equal to L over L naught minus 1. For the true strain length for a specimen, change at every instant of the increment, let's say delta E1 is equal to delta L1 over L1, Change in length 2 mean the strain 2 is equal to delta L2 over L2. Strain 3 at the third load location, change in length 3 over L3, and so on. If we'll sum up like this, that Et is equal to sigma I is equal to 1 till n, then the equation becomes like delta Li over Li, and if we'll take integration of this, L naught is from L to L naught, and there is a change in length to the original length, to the length. Okay, so true strain will becomes, in this case, Et, which is true strain, is natural logarithm of 1 plus engineering strain. It means the true strain is a function of engineering strain. Now let's discuss about the concept of proof stress and how to calculate the proof stress through stress strain diagram. Most metals do not have the yield point in stress strain diagram or in stress strain curve. Hence, to determine the elastic limit is very difficult. In this case, we have to use proof stress, which is at 0.1% or 0.2% of strain method, or 0.2% of the strain value. It means there will be some permanent deformation which is equal to 0.1% or 0.2%, which is already known value. This is the value that produce very small plastic deformation, and we have to use this graph to calculate the proof stress, which is known value, and it is very small plastic deformation in the material. As we can see in the graph, let's say this graph is for a specimen or a sample of length 1 meter, which is equal to 1000 millimeter, and 0.2% of that 1000 millimeter is equal to 2 millimeter. So draw a parallel line to the proportional line or proportional limit of stress strain curve from a 0.2% offset point, which is 2 millimeter length of a sample of having a total 1000 millimeter of length, and the point where this line crosses the stress strain curve, that point will be a proof stress of that material. Hard steel or non-ferrous material or metals do not have defined yield limits. Therefore, the stress corresponding to definite deformation, which is either equal to 0.1% or 0.2%, is used instead of yield limit. So this stress or this proof stress is called offset yield limit or proof stress or the yield point of that material. In this case, the proof stress will be equal to the material yield stress. Hope you understand the concept of proof stress. Stress strain diagram or stress strain curve for different metals is different. Let's say we have 4 specimens, and the specimen 1, which is here you can see, shows an example of a brittle material breaking at yield with a very low strain value. Hence, the brittle material have minimum plastic deformation. It will fail suddenly and catastrophically once ultimate tensile strength of the material exceeded. Let's move to specimen 2. Specimen 2 shows an example of ductile material like low carbon steel with stress increase after yield point. This is the yield point and stress increases after the yield point. For specimen 3 shows an example of stainless steel material without stress increase after yield point. So after this yield point, stress decreases and strain increases. And specimen 4 shows an example of soft elastic like aluminum material breaking at a large strain point. Here the stresses developed in a material is very less, but strain developed in a material is very high. So just to show you and to give you a clear concept that why we need this stress strain diagram and what are the benefit of this stress strain diagram, and different material have different stress strain values. So modulus of elasticity E for different material is also different. So carbon steel has expansion coefficient of 0.11 millimeter per meter per degree centigrade, and the melting point of carbon steel is 1425 to 1540 degree centigrade. Stainless steel has the expansion coefficient of 0.17 millimeter per meter per degree centigrade, and the melting point is 1510 degree centigrade. Similarly, the GRE and GRP has more expansion coefficient of 0.216 millimeter per millimeter degree centigrade as compared to carbon steel and stainless steel. So example of thermal expansion rates over a temperature range of 0 to 82 degree centigrade: carbon steel is equal to 1 millimeter per meter, copper is 1.34 millimeter per meter, and stainless steel is 1.34 millimeter per meter. It means carbon steel expand 1 millimeter per meter up to 82 degree centigrade. Copper expand 1.34 millimeter of 1 meter length when the temperature increase from 0 to 82 degree centigrade. Similarly, stainless steel increases 1.34 millimeter of 1 meter length. Change in temperature is from 0 to 82 degree. This is the basic things to give you an idea and the concept, because it will plays a major role when we will perform the formal stress analysis, and it will give you a better understanding when different materials are being used in a piping system, and it will show a different results in stress analysis. Now, the application of stress and strain curve. Stress strain curve helps in understanding a material mechanical properties such as its yield strength, ultimate tensile strength, Young's modulus, Poisson's ratio, and toughness of the material. It also helps to calculate the allowable stresses, the proof stresses in case yield point or yield strength of the material is unknown, as we discussed earlier. It also helps engineer to select appropriate material for different applications. This stress strain curve also ensures the strength and to make sure that the material can withstand the expected load and the stresses for its entire design life without failure. This stress strain curve is also useful in assessing how material will behave under various loading conditions during design and operating scenarios. Most of the manufacturers use stress strain curve to ensure the consistency and quality of the material, as the deviation from expected curve might indicate defect or inconsistencies. I hope you would understand the concept of the different type of forces acting on a piping system, different kind of stresses develop in a piping system because of those forces. What is the relationship between stress and strain? How the stress and strain can be calculated? What is the stress strain curve? And what is the engineering stress strain curve? What is the true stress strain curve? How to calculate the proof stresses for materials, those who do not have the yield point, and what are the application of stress strain curve, why we are using it, and why we are calculating stress and strains. Let's discuss in detail in next video about stress and strain in a piping system with respect to different kind of loadings. Thank you.